So I would say good morning because I'm still jet lagged from 2 days ago. I'm Ahmed Youssef, a software design engineer at Valeo. I'm working there since 2015. Me and my team are working on how to virtually validate systems and functions using some simulation platform. We are working now more on the LiDAR systems, and I'm here to present how we are doing it, to discuss some ideas, so it will not be that long, so I can open some more discussion, let's say discussion points. So when we started transporting stuff, we go from place to another, we were using horses. With more demand that we got, we needed more horsepower. So what Benz did, he virtualized the horsepower, so what we called a car. It was 1886, south of Germany. And not long time ago, we were driving in couple. So you were going, you with your husband, your wife, your girlfriend, and she was always, or he was always nagging about going to the bathroom, coffee, navigating, waking you up. And with technology, we virtualize the co-driver or your wife, and now the GPS is navigating you, other systems are waking you up, telling you to take a rest, and some other systems. And with further development, I would say rapid development, we are going to what we called a full autonomous driving. So this is a video from Audi.AI, the 2018 one. It has multiple sensors, long range, short range, laser scanner, ultrasonics, cameras, MMIs, roof antennas, and GPS. And it could reach level 4 autonomous driving. It was tested for that. I would say 3.5. It can navigate, it can change the lane without a driver attention. It can also detect traffic jams and so on. I will not continue it because it's too long. So what are the software challenges? As we know, we have more than 25 driving assistance systems, which are basically, the objective is to increase the safety of the driver and the road. As I said, there are long range, short range, radars, LiDARs, ultrasonics, and this is what we call sensor fusion. A presentation yesterday was saying that sensor fusion is in the gray area. It is true, because we need to really validate it, because to ensure the functionality, we need to abusively test the functions which have this sensor fusion. And this topic is, as we know, it's ISO 26262, which is on the other side of this foyer. And in order for us to test such functions, we need to use dynamic testing, or we use the model-based testing. And the idea behind Auto.AI is also to test the artificial intelligence algorithms. So what are the challenges? First is cost. According to Ford, a prototype costs 250,000 euros, only to develop and manufacture one car. Gas, human resources, depreciation are more cost on this, or more overhead on this. The time consumption regarding testing in an autobahn, highway, the manual testing, the automatic testing, and so on. And last, the more human resources we need, the more time we consume, the more cost and the more budget we need. In addition, accidents such as NCAP, accidents on the highway, the same what happened 8 months ago with Uber. These are all challenges which we are facing, and the last, but not least, is the artificial intelligence algorithm. Now companies are challenging themselves and others to drive as many miles as they can. Waymo in July 2018, they said they could drive 8 million miles, and now they are counting. I think they could reach 9 million very easily. And in order to face this challenge, we said, okay, why not? We can virtualize everything. The environment, the ego vehicle, the driver, the co-driver, the algorithm, and the scenario. So this is the solution. First, we developed our own ADAS model-based testing. The model-based testing means it's a tool or a platform which can generate as many test cases as possible. Why? In order to cover test cases, requirements, customer tickets, corner cases, and to ensure traceability. On the other hand, we have the test model. The test model is the algorithm which we want to test, such as our AI artificial algorithm or any other system, algorithm, or function we want to test. And at the end, we have the simulation tool. The simulation tool is able to simulate your ego vehicle, your surrounding, your sensors, your sensor physical model, and other scenario, let's say, parameters. And integrating all of them, which gives us this virtualization or this virtual validation concept. I would just say I will give you 3 examples what we do at Valeo. So first, we have a model-based testing. This tool now is able to control the simulation tool. It will generate the test scenario, such as a parking scenario. It will put the right parameters, such as distance, parking slot, where is our car, and so on. And with any interface, it will just say, okay, I want a test case where the vehicle speed is X kilometer per hour. And this will be set on the simulation tool. We'll see it in the next slide. And this simulation tool will react to this model-based testing. And now the test case has a parameter which says, okay, the vehicle speed is X kilometer per hour. After that, the steering wheel angle should be retained from the simulation tool, and this is what will be done. Now, actually, what the model-based testing is doing is building the scenario in order for us to test it on SiL or HiL. And it will send the steering wheel angle back to the model-based testing and so on. And at the end, we have a very complete set of test cases for a parking slot, as an example. One more example is if we get not a system, but a function, such as object tracking, object classification, and so on, we generate a deterministic behavior scenario. We put them in a very, very big database, and we start feeding them to our algorithm. When we're feeding them to our algorithm, let's say it's either an AI algorithm or it's a normal algorithm, we'll get some reactions which will be able us to study how this artificial intelligence brain work. So let's go a bit deep in this. So what we do, we have a simulation tool. It could be ROS, it could be CarMaker, it could be RF Pro, it could be any vendor simulation platform. We feed this information inside our software in the loop. It can be any real-time framework, or it could be feed it to the HiL. We have our own HiL system, but it could be also DSpace. It could be any vendor HiL. In this HiL and SiL platform, we have our neural, or we have our algorithm. And at the same time, we generate the ground truth. With simulation tool, the ground truth is very easy, but we generate them with different formats, such as Veloces or some XML formats and so on. And the model-based testing, in this case, will be responsible for testing this scenario and the reaction of our SiL and HiL algorithm. After that, okay, the report is generated, and we get, of course, 2 sets of outputs. One of them is a valid one, and one of them is invalid one. The valid one can be again used as a training set. It's a new training set for your neural network. Why? Because it was successfully valid, and your neural network successfully detected your pedestrian, your parking slot, and so on. And this is now what we are working on ultrasonic cameras as only a proof of concept. I will show you one deployment of auto parking at Valeo. This is our own simulation tool. At first, We will just run our model-based testing and our canoe. Our model-based testing is based on Java. It's a multi-threaded model-based testing tool which generates as thousands of cases as possible. And now, as we can see, we have here a curb. I just put a normal curb, and we'll see how our algorithm will detect the parking slot. So these are ultrasonic sensors, and our model-based testing is retrieving these distances. Well, it couldn't find such a slot, so the maneuver was canceled. Now what I did is I only removed the curb, and now we'll see on this attempt, it will park in one time, without reversing forward, backward, and so on. So the first edge was detected. And now the parking slot was detected. So this is our parking slot. And it will go to a perfect S-curve in order to park in this parking slot. So this was one example of how to deploy this on an artificial intelligence algorithm. But now we are working on a new concept. So this is a tool. It is Car Maker. Now, what we are concentrating on is to validate the neural network algorithm. But why don't we do the other way around? Why don't we train our validation toolset to validate a normal algorithm? And this is what we did. So on a simulation platform, you can actually develop a sensor model which behaves or depicts your sensor. For an instance, a laser scanner, a LiDAR. So what we did, we actually trained our sensor model to behave the same as our laser scanner, which means the hardware limitation are there, the software limitation is there, everything is there, and we can see on this screen that we generate the point cloud as it's real, not the other way around. And now what we do is we are testing a normal algorithm, not an artificial intelligence trained algorithm. How can we do this? We try to record as many traces as possible and train a sensor model to behave as the laser scanner and not the other way around. And this was the result behind this. This was in a very perfect weather. So we can see the ground reflections are nice, everything is nice. And then when we go to a foggy or rainy weather, we get such, I don't know if you can see this. We get some ground reflections. Yeah, I don't know if you guys can see this, but we can see that the ground reflections are different. We can see the lane markings are different. We have some reflections there because it's rainy, and so on. So this is now the trend that we are trying to drive, that we don't need an algorithm or a system which is trained. We also need a validation platform which is trained. And yeah, basically what I said, that I wanted to show you what we are doing, what is our trend in our team, and what we are trying to do. So after all, the summary is we should always develop our sensor model and at the same time test it, deploy it again, and we go to this loop. So the V model is, I would say it's not anymore always valid. It is sometimes valid, but the iterative fall or the iterative waterfall is now more valid, or this is the trend what we are trying to go through, because what we see, as we saw in last slide, that every time if we have a valid data set or a training set, we can actually train another sensor, another ECU, another function to behave as a new neural network. So this was the end of my speech. Thank you. I would like to listen to more questions than the presentation. Thank you.